Lab 5 Magnetic Braking with Faraday by Pablo Vila. The purpose of today's video is to collect observational data of a falling magnet through a conductive tube, model the magnet and tube interactions computationally through GlowScript, and compare the computational predictions to observed data. The main lab results we'll see by the end of this video is 1. The average magnet fall time observed is 1.216 seconds, the average magnet fall time computed is 1.219 seconds, and the error is 0.246%. The main physics ideas that are present in this experiment include the magnetic field of a bar magnet as seen below. This equation shows the magnetic field of a bar magnet at any location. The second equation we'll go over is Faraday's law, which is EMF equals the integral of E dot dl, which is equal to the change in magnetic flux. And then finally, we'll look at Lenz's law, which is essentially the negative sign shown in Faraday's law. The procedure in this experiment includes determining the north side of a bar magnet. We can accomplish this by using a magnetometer app on your phone and figuring out what side of the magnet repels the magnetometer value. Next, we drop the magnet from the top tube with the north side facing down. We calculate the time it takes for the magnet to drop and run the trial 5 different times to get an average. The initial conditions in this experiment include the tube length, which is 0.32 meters, tube width, which is 0.0045 meters, the tube inner radius, which is 0.0145 meters, and mu magnet, which is 1.82, and this value was found from our lab 3 results. The system in this experiment is the magnet, and the surroundings include the aluminum foil and Earth's gravity, along with everything else in the world. As you can see from the 5 trial runs in this experiment, the average fall time of the magnet was approximately 1.216 seconds. Next, we'll analyze the code that gave us the computational solution to this experiment. We can start by defining all constants and initial conditions in this experiment. This includes values such as mu naught over 4 pi and the length and radius of the aluminum foil. Next, we define 2 functions, the magnetic field of a dipole and the change in magnetic flux in the aluminum foil caused by the falling bar magnet. I want to highlight that the equation in line 99 is the equation to find the magnetic field at any location in space, and the equation found in line 116 and 117 are Faraday's law. Finally, we can find the induced current and induced magnetic field at each ring of the aluminum foil caused by the falling magnet. We find the magnetic force on the magnet by the induced foil. Line 180 finds the net force on the magnet found through time. The results of this code show that the magnet should fall in 1.219 seconds. The graph starts with a steep decline to show the accelerating magnet before it enters the tube, and it flattens out after it falls at constant velocity through the aluminum tube. The blue and red colors show the induced current through the aluminum foil that are equal and opposite in magnitude. One of the currents is the induced current of the foil, and the other is the induced current of the magnet. And that's why you can see that one is rotating clockwise and the other is rotating counterclockwise. What if the resistivity of the conductor were reduced as close as possible to 0? The magnetic force would be very, very strong, likely preventing the magnet from entering the tube at all. This goes back to Faraday's law and Ohm's law. A low resistance means there will be a large current, and a large current means the magnetic field of the bar magnet will be large. Thus, the magnetic force will be very, very strong. What if there were holes or slots cut into the tube? The magnet would fall faster due to a break in the induced current of the foil. Thus, gravity would be stronger than the magnetic force, and the bar magnet would fall faster. In conclusion, the falling magnet produces a curly electric field on the aluminum tubing because of Faraday's law. This produces an induced current that produces an induced magnetic field. Thus, a force is exerted back on the falling magnet. Some potential sources of error include the aluminum tubing was not thick enough to exert a strong enough force. Timing of the falling magnet was not perfect, and an inaccurate mu value was calculated during lab 3. Thank you everyone for the massive support I have received throughout these past 2 semesters. Unfortunately, this will be my last video because I have not been receiving enough likes on my previous videos. Once again, thank you, and please like and subscribe.